Okay, let's consider our third and final example for today's lectures. In this case, in addition to doing a hypothesis test, I'm also in section 2 here going to have you compute a confidence interval. So this is a great opportunity to try to review, a good opportunity to self-test. How is the stuff from last week sitting with you? Do you still understand it? Do you know the steps? And then in the last case, it's just a little bit of a concept question that we'll consider as well. Now, at this point, you've seen quite a few examples of hypothesis testing and confidence intervals. So I think it's a great idea to just pause the video and actually try to do questions 1, 2, and 3 before seeing the solution. All right, here's our solution. The data to the left is a simple random sample of dinner bills. We want to use a significance level of 4% to test the claim that the mean dinner expense is $193 or less. So again, we're dealing with a mean, so our hypotheses will be regarding the population parameter mu. And we're looking at a claim of mu less than or equal to 193. Remember, the equal part, or the less than or equal, always goes with our null hypothesis. So our alternative hypothesis in this case is that the actual mean dinner bill is greater than $193. Looking at these pairs of hypotheses, we know that this is corresponding to a right-tailed test. Remember, again, you look at your alternative hypothesis in order to figure that out. As a right-tailed test, our extreme region, or the place where we're going to look for our p-value, is going to be to the right of the test statistic we end up computing. So inside of Excel, for type of test, we would say right-tailed test. And we know that in terms of computing our p-value, this is going to look like probability that t is greater than some sort of number. And the number that we're going to eventually put in here is the t hat that we need to compute. All right, so at this point, we use the data to compute our sample statistics, and then we'll use our t hat formula to compute our test statistic. So usual Excel commands. Oops, forgot the equal sign in front of this, and then count. All right. Computing my denominator first. Again, just breaking up the formula into simpler steps. I have a denominator, now I can look at the top. This is the difference between my x bar and my claimed mean, and then divide by that standard error, that denominator term. So get a test statistic of 2.147. Now we know that our probability for the p-value is going to be probability that our t distribution is greater than 2.147. And since that's a greater than, we have to do the 1 minus trick. And so we know when we compute this p-value, we're going to do a 1 minus t.dist. Select our test statistic. Degrees of freedom is going to be 85, right? 86 minus 1, and then true. So our p-value in this case is a 0.017. Our alpha value is a 0.04. And so once again, p-value is less than alpha, so reject H0. I realize we haven't done any examples where we failed to reject H0, but they are coming, so we'll see them soon. All right, finally, let's write our conclusion. So in this case, we have sufficient evidence to conclude that, so we're rejecting H0. The mean dinner bill at our hotel restaurant is in fact greater than $193. Okay, in our next step, or in our next problem, I should say, we want to compute our confidence interval. So if you haven't already attempted this, again, pause the video, test yourself, do some self-testing here, see if you can create the confidence interval for the mean dinner bill at this hotel restaurant. Okay, for question 2, we're going to create a confidence interval with a confidence level of 94% for this mean of all dinner bills at our restaurant. So we've rejected the claim above, but maybe now we're admitting, we don't know too much about this mean dinner bill, so why don't we construct a confidence interval for it? Again, pause the video and see if you can work out your solution for this, and then you can hit play again and get the final solution. All right, so as a review, remember that we need to have some sampling statistics when we're working with our confidence interval. And we can actually just copy and paste from the sample statistics we computed above. So rather than doing the whole average, stdev, etc., we can just cell reference, and that cell reference will drag down to give us our nice standard deviation and sample size. So you can see that we're matching up pretty nicely over here. If you don't like that the n value has been formatted as a $, you can change it. You can also change the rounding, so this is just a nice whole number. So remember that your confidence interval has two components. We have the sampling side, right, where we need x bar. This is going to be the center of our confidence interval. And the s and square root of n, these are going to be involved in determining our margin of error. So in addition to our margin of error, we also need a critical value, or I should say to compute our margin of error, we also need a critical value. This starts at the confidence level, from which we determine alpha over 2. And remember, in this case, since we're constructing a confidence interval for a mean, we should use a t alpha over 2. And this is consistent with the hypothesis testing. So if you're using the t-distribution for hypothesis testing, you should use the t-distribution for your confidence interval as well. All right, so our confidence level is 94%. Alpha is going to be the missing percent, so 1 minus your confidence level. Cut that in half to divide this over the two tails. So even though your hypothesis test was a one-tailed test, it was a right-tailed test, confidence intervals are always two-tailed, so we're always going to do this division by 2 trick. Finally, t alpha over 2, remember this is our t.inverse command, and 1 minus alpha over 2 is the area to the left. Our degrees of freedom are going to be 85, right, n minus 1. And so we'll have a t alpha over 2, a critical value here of 1.906. Our margin of error formula looks like t critical, t alpha over 2, times sample standard deviation over the square root of n. Again, these formulas are on the front of the exam, so you should just make sure that you know how to use and understand the symbols that are inside of the formulas. So we're going to take our sample standard deviation, or sorry, we'll start in order. We'll go with our critical value first, times our sample standard deviation divided by the square root of our sample size. And this gives us our margin of error. So our margin of error here is about $7.45. The confidence interval estimate for that mean then becomes x bar minus the margin of error. That gives us our lower bound. X bar plus the margin of error. This gives us our upper bound. All right, so we can be 95 or 94% confident that the population mean dinner bill, right? So the mean dinner cost in the population is between 193.94 and 208.85. So somewhere right around $200 seems to be the best guess here. And we can see why the initial claim that it's less than 103, or sorry, less than 193 would be rejected. All right, last question, number 3. In your own words, explain why the mean of all dinner bills is different than the sample mean we compute using that average A2 to A87. So in other words, why is this sample mean, generally speaking, different than the actual population mean? So this is a really good exercise to try to put this in your own words. Think about what we've been working with over the past 2 weeks, actually, from sampling distributions into confidence intervals into hypothesis testing. Try to explain why this works. Why is the mean of all dinner bills, this population parameter, generally speaking, going to be different from the sample mean that you collect as a researcher? All right, so let's answer the question. A picture's worth 1,000 words, so I'm going to refer back to a visualization that we looked at the beginning of the course. Here, let's pretend we know the diastolic blood pressure for an entire population of people. And each green dot represents a person, and if you look over at their height, this is their diastolic blood pressure. The reason that your sample means end up being different from your population mean is because you're randomly selecting a snippet of that population to represent everybody. So in this case, I'm selecting 15 participants and then using that to compute a sample mean. And since the sample itself, right, which blue dots are which people I end up including in my research, since that is randomly determined, in a sense, so is the sample mean that I'm going to get. It's the central limit theorem that tells us that these sample means tend to be pretty close to the population mean in green, although we shouldn't expect them to be equal because we're not considering the entire population. We're just working from a small little sample taken from the population. So what do we write for example 3? Well, the important thing is to put this in your own words. I can't stress enough how important it is to summarize things in ways that make sense to you. This is how you actually learn and retain information. So I'm not going to write an answer in this case. I want you to write your own. And maybe even post it to Piazza and see what other people think. Okay? So this is a really great exercise to understand. This is fundamental to why we need statistics, right? This idea, why is the population parameter different from the sample mean that you end up collecting? This is foundational to why we need statistics. So it's a really great exercise to put this in your own words. Write a nice paragraph, and if you want to have it looked over, feel free to contact me or post it to Piazza and we can discuss it. All right, great work today.